Welcome to today's lesson, which will serve as a brief introduction to solutions chemistry. In this lesson, we're going to first review some key terms, and then we're going to discuss the behavior of salts, and mostly salts or ionic compounds, in aqueous solution. Aqueous derived from the term aqua, meaning water. That said, the first term that we're going to define is solubility. So again, solubility is defined as the ability of a substance to dissolve in a solution. The solution does not necessarily need to be water-based. However, oftentimes it is. So there are other solvents like ethanol or oil-based solvents. However, for the purpose of this lecture, we're going to focus on aqueous or water-based solutions. Insoluble, again, is the opposite prefix indicating the opposite of the aforementioned word, meaning that this will not dissolve in solution. SOLN is my abbreviation, or a common abbreviation for solution, because if you say it really fast, it sounds like solution. Next, a precipitate. A precipitate is the result of mixing two or more liquids, and the precipitate describes a solid that can potentially emerge from it. So this is an insoluble solid. That emerges from a liquid solution. All right, so first we're going to discuss some ionic substances and how they behave in water and how to represent them. So first, I fill my beaker up with some water, and we have a NaCl. So as I shake NaCl into the water, we all know that salt will dissolve in water because we've observed it before and we see it in salt water. So what exactly happens to the ions within NaCl? We're not going to discuss the way the water molecules separate the compound today. We'll save that for a later date. However, for right now, just know that NaCl will separate into its respective ions. That means that we will see sodium ions floating in the solution as we will see chlorine ions floating in the solution. And we'll just draw a few to represent where they may disperse themselves to. Okay, now in order to represent this mixture, we oftentimes sketch a net ionic equation or an ionic equation. In this case, the ionic equation would represent the addition of sodium chloride, which is a solid. The letter S indicates that we are adding the solid state of sodium chloride to the water. And that is going to dissociate into an Na plus ion, because sodium is one of our group 1 metals, and then chlorine will dissociate into its 1 minus ion because it is one of our halogens. Na plus, and then we're going to add the AQ to indicate that it's now dissolved in water, plus Cl minus, which is also AQ or aqueous. Okay, now what happens if we mix two separate salts that are soluble? In this case, I have two scupulas sitting here. And in one scupula, we're going to add salt again. And in the second one, we're going to add calcium nitrate. Now, as we all recall, calcium being a group 2 metal, nitrate having a charge of 1 minus, that means that calcium's 2 plus charge will require Ca2NO3 1 minuses per 1 calcium. So as we pour both into the water, again, ignoring how they separate, how the water separates them, we're just going to know that they're going to separate into their respective ions. So sodium, again, will separate from chlorine, and calcium will create its 2 plus charge, or maintain its 2 plus charge, whereas nitrogen in NO3 will maintain its charge as well. So these all separate, and they intermingle, they bump into one another, and since none of them are really attracted to one another, they're going to continue to exist as they are. So again, in order to represent this net ionic equation again, or just the ionic equation again, we will sketch NaCl, and again that's in its solid state, plus Ca, NO3, and again we determined that there were 2 of them because calcium has the 2 plus charge, and nitrate, we all memorized, has the 1 minus charge. And these will all, again, separate into their respective ions. So we will have a sodium ion floating, and that is aqueous. We will have a chlorine ion, that is also aqueous. We will have a calcium ion, also aqueous. Now, in order to balance this, we're going to, for every 1 calcium ion, have 2 nitrate ions. And that is also aqueous. Running out of space on the page. That happens with these. Okay, so as we noticed, these are balanced. I could not simply add another subscript at the end because if I put a 3 or a 2 behind that 3, it would look like we had 32 oxygens for every 1 nitrogen, and that is not the case. So instead, what we're going to do is indicate that we have 2 with a coefficient. All right, so we've taken a look at a couple of ways to represent ionic substances as they behave in water when they dissociate or when they're not attracted to one another. In our next example, we're going to take a look at what happens when you mix 2 ionic solutions that have a pair of ions that they're attracted to one another. So in the case below, we're going to look at what happens when we mix a silver nitrate solution. So we have Ag plus and NO3 minus. In that solution, this is a little disposable micropipette, if you can't tell. And we're going to mix that silver chloride with a salt solution. So in here we have Na plus and Cl minus. Now, I'm going to mix both of these in water, and we're going to see what happens. As we mix them, we're going to recognize that silver and chlorine have a strong attraction to one another. So nitrate will separate, sodium will separate, silver will separate, chlorine will separate, okay, so as they separate and they start to intermingle with one another, we're going to recognize that silver and chlorine have this strong attraction to one another. They will be bound to one another, in fact. The attraction between silver and chloride is greater than the attraction between their respective ions in water. form what's called a precipitate, and they will fall to the bottom of the solution, and it will appear as though a solid is formed in that solution. In fact, that is what happens. As the silver and chlorine are attracted to one another, they are heavier than the water or more dense than the water, and so they will fall and create a visible, in this case, white murky substance. In order to represent this, we can represent it just as we did above. However, in the product side, there is not another, they don't separate. Instead, the silver and the chlorine will remain together. So, as we start, we have Ag plus, and that's aqueous, plus NO3 minus, also aqueous, and we're going to add that to sodium, aqueous, plus chlorine, and that's going to produce Na plus, that's still aqueous because it's still mixed in the solution, plus nitrate, which is also still aqueous, plus our last thing, which is our insoluble solid or our precipitate, can be represented two separate ways. It can be represented as AgCl as a solid, or you can indicate that it's a PPT for precipitate. Now, if you were asked to write the net ionic equation, the only thing that we're concerned with is silver chloride. So we can eliminate the rest because whatever's on the left side of the equation is also present on the right, meaning that it did not change. So the only change here is between silver, chlorine, and silver chloride. So the net ionic equation would then be Ag plus aqueous plus Cl minus, also aqueous, yields AgCl, and here we're just going to write PPT just to be different. All right. Now, wouldn't it be nice if we were able to predict whether a compound would form a precipitate without having to mix the chemicals together? Well, fortunately, people before us have discovered that there are trends that can be found and identified within certain ions. So they've put together what we call a general solubility rules chart, or a solubility rules chart. As a rule, all nitrates are soluble. That means that anything that's bound with nitrate will dissolve in water. Now, with most of these rules, there are a few exceptions, and solubility is on a sliding scale. So for our purposes, we're just going to concern ourselves with general atmospheric conditions and not consider any other external factors that could affect the ability for something to dissolve. So we will learn these at 25 Celsius and 1 atm. That said, all nitrates are soluble. Additionally, all acetates are soluble with water. As we notice, silver acetate is moderately soluble, which means that it will mostly dissociate, or it will somewhat dissociate, but mostly stay together, remain insoluble. Anything with chlorine, bromine, or iodine. All chlorides, bromines, and iodines are soluble except silver, which, as we see here, it was soluble before. Now, when chlorine mixes with silver, it becomes insoluble and forms a precipitate. Lead and mercury. Additionally, sulfates are soluble except those in barium, lead, and calcium, and strontium. Next, carbonate and phosphate. All carbonate and phosphates are insoluble except those of sodium, potassium, and ammonium. So, if you see a carbonate or phosphate, likely that will remain as a solid. All hydroxides are insoluble except those of sodium, potassium, and hydroxides of barium. as a solid in water, except those are sodium, potassium, ammonia, and those are the alkaline earths. And then lastly, all salts in the sodium ion, potassium ion, and ammonium ion are soluble, except for several uncommon ones, which we will not concern ourselves with. Now, that said, using this chart, we should be able to predict what will happen, or the state of each of our aqueous solutions after introducing one to the other in a solution. So we'll do one last one where we will take a look at what happens in predicting whether or not we form a precipitate. In this beaker, we have water, and we are going to take 2 dropper bottles, and in 1 dropper bottle, we are going to mix silver nitrate, aqueous silver nitrate, with, we'll pick sodium acetate. Okay, as we mix these will separate Ag plus, NO3 minus, Na plus, C2H3O2 minus, etc. Now, let's check to see if these will remain dissolved in the water or if they will find a partner that they're attracted to. As we see, nitrates, all nitrates are soluble, so silver nitrate is soluble. Anything with nitrate is soluble, so that means the sodium nitrate is also soluble, which means that they will also remain mixed in the water. Next, all acetates are soluble. Silver acetate is only moderately soluble. So as we see, silver and acetate are together. It's only moderately soluble, so for our purposes, we're going to consider it insoluble. So in this case, silver and acetate are pretty attracted to one another, fairly attracted to one another. It's like we're not going to go there. Okay, so when we're writing our net ionic equation, first we're going to write out the full ionic equation, which is silver aqueous, because it's mixed with water, plus nitrate, aqueous, because it's mixed with water, plus sodium, aqueous, because it's mixed with water, plus acetate, C2H3O2, aqueous, because it's mixed with water. And we're going to form our sodium and nitrate, which are not too interested in one another, plus NO3, also aqueous, plus our insoluble salt, moderately insoluble, AgC2H3O2, and that will be our solid. Now, again, when finding our net ionic equation, we can ignore sodium, we can ignore nitrate, because they're present on both sides. So, we're going to take a look at silver plus acetate, C2H3O2 minus, and that forms our precipitate, which is soda, C2H3O2 minus, and again, that's our solid. All right, last one that we're going to take a look at is this beaker here, and we've got a couple of dropper bottles, meaning that we're going to mix a aqueous solution with each of them, and we're going to add silver chloride. Nope, I'm sorry, not silver chloride. We're going to add lithium chloride with calcium bromide. Calcium bromide. Bromine is a halogen calcium group 2 metal. That means CaBr2. So, fill it with water, mix them. Calcium will separate into its charge. Bromine, lithium, chlorine. Now, as they interact with one another, none of these, according to our solubility rules, are very attractive to one another. As we can see, all chlorides are soluble, all bromides are soluble. So chlorine and bromine are not going to want to boogie much with calcium or lithium if given the opportunity. So, in this case, our ionic equation will be calcium plus bromine. We got to balance this, so there's 2 of those. Plus lithium, plus chlorine, produce the same gosh darn thing because nothing changed. So we've got calcium. We've got 2 bromines. Plus lithium, plus chlorine. All right. Now, if we're writing our net ionic equation, nothing changed. So we don't really have to sketch that, since nothing is soluble in the water, or insoluble in the water. Everything is soluble. All right, last one. What happens when we add silver chloride to lithium bromide? Well, as we see, silver chloride is one of our exceptions with chlorine. And as we recall, all chlorides, bromides, and iodides are soluble except silver, lead, and mercury. So in this case, nothing is going to happen because silver chloride will remain as a precipitate. And since lithium and bromide are not too interested in one another, let's